Hello there, and welcome back to Bedtime Science. I am really glad you are here tonight. Somewhere nearby, a clock may be counting. It may be a digital clock whose numbers change without sound, a watch divided into tiny regular intervals, or an invisible clock inside the device carrying this voice. Even if the room is completely quiet, time seems to be present. It seems to pass through the room, through the body, through the night, carrying one moment away and replacing it with another. We rarely question this movement. A second ends, another begins. The past appears fixed behind us. The future seems open ahead. The present feels like a thin, illuminated line traveling between them. We remember yesterday, experience now, and wait for tomorrow. But physics has made this simple picture increasingly difficult to defend. There is no single universal clock shared by the entire universe. Two observers moving differently can disagree about how much time has passed, and both can be correct. Two events that happen at the same moment for one observer may not be simultaneous for another. A clock closer to Earth ticks at a slightly different rate from a clock higher above it. Near a black hole, the disagreement becomes enormous. At the deepest level of some attempts to combine gravity with quantum mechanics, time can even disappear from the equations. And yet breakfast still becomes lunch. Children grow. Stars age. Memories accumulate. A glass can fall and shatter, while shattered glass never gathers itself from the floor. The universe appears to know a direction. Tonight, we are going to follow that contradiction slowly. We will begin with the clocks humans built to catch time, though time itself could never be placed inside them. We will watch sunlight cross stone, follow pendulums through dark rooms, sail with navigators who needed accurate clocks to find their way home, and stand on railway platforms where every town once kept a different noon. Then we will enter Einstein's moving trains, carry atomic clocks around the world, climb through gravitational fields, and approach places where one observer's minutes become another observer's years. After that, the story becomes quieter and stranger. We will ask why the past differs from the future, why memory points in only one direction, why disorder tends to grow, why the laws of physics often seem almost indifferent to which way time runs, and whether the flowing present exists outside human experience at all. There may not be one final answer. The word time is used for several related things: the number measured by clocks, the order of events, the geometry of space-time, the direction created by entropy, the rhythm of a living body, and the feeling of duration inside a mind. These may be different faces of one reality, or they may be layers that emerge from something deeper. For now, the clock can keep counting without explanation. The earliest clocks did not tick. They cast shadows. Long before mechanical gears, people watched the repeating changes in the sky. The sun rose, crossed the heavens, and disappeared. Shadows shortened toward midday and lengthened toward evening. The moon changed shape. Seasons returned. Certain stars vanished and reappeared. Time was first recognized not as an invisible substance, but as repetition. A day was not originally a precise container holding 24 equal hours. It was the recurring cycle of light and darkness. Many early systems divided daylight and night separately, so an hour of daylight could be longer in summer and shorter in winter. The length of the hour changed because the purpose was not to create a universal scientific unit. The purpose was to organize life around the sky. A sundial makes this relationship visible. A raised edge or rod casts a shadow across marked lines. The moving sun changes the shadow's position, turning astronomy into a local clock. But the reading depends on place, season, and weather. A sundial works because Earth rotates, although for most of history people described the sun as moving across the sky. Water clocks created a different kind of rhythm. Water flowed from one vessel to another, and the changing level marked duration even indoors or at night. Sand clocks later used falling grains. Candles could be marked at intervals, and allowed to burn. Incense clocks measured time through slow combustion. Each device relied on a process that changed in a reasonably repeatable way. The clock did not contain time. It contained motion. This remains true of every clock ever built. A pendulum swings. A quartz crystal vibrates. An atom changes between energy states. A clock is a physical system chosen because some part of its behavior repeats reliably enough to count. That is already a clue. Science does not measure time directly in the way a scale compares masses or a ruler compares lengths. It compares change with change. A certain number of swings accompanies a heartbeat. A certain number of atomic oscillations accompanies a chemical reaction. The word second names a relationship between processes. For centuries, the rotation of Earth provided the most important standard. Noon was connected to the sun reaching its highest point in the local sky. But Earth is not a perfectly regular clock. Its rotation changes slightly because of tides, movements within the planet, exchanges of angular momentum with the atmosphere and oceans, and other effects. The old celestial clock is magnificent, but not exact enough for the most demanding modern measurements. Before atomic time, however, the greatest challenge was not the irregularity of Earth's rotation. It was carrying accurate time across the ocean. To find latitude, sailors could measure the height of the sun or stars above the horizon. Longitude was harder. Longitude is connected to the difference between local time and the time at a reference location. Earth turns through 360 degrees in roughly 24 hours, so a difference of 1 hour corresponds to 15 degrees of longitude. The principle was simple. Keep a clock showing the time at home. Determine local noon by observing the sun, compare the two. The difference reveals how far east or west the ship has traveled. But a clock on a ship had to survive changing temperature, humidity, movement, salt, friction, and months without repair. A small daily error could become a dangerous mistake in position. In 18th century Britain, the longitude problem became a national concern after maritime disasters and the loss of ships. Parliament offered substantial rewards for a practical method. Astronomers pursued lunar observations. Clockmakers pursued precision. John Harrison, a carpenter and self-taught clockmaker, spent much of his life building marine timekeepers. His early sea clocks were large machines with carefully balanced mechanisms designed to resist the rolling of a ship. Later, he produced a smaller watch-like instrument of extraordinary accuracy. Harrison's work was not simply a better clock. It changed the meaning of position. A ship could carry the time of one place into another, compare two noons, and locate itself on an invisible grid. Time had become geography. This connection remains inside modern navigation. A satellite positioning receiver calculates location by comparing the arrival times of signals from several satellites. Because light travels at a known speed, tiny timing differences become distances. An error of a billionth of a second corresponds to roughly 30 centimeters of light travel. Accurate position requires accurate time. The navigation system in a phone is therefore also a network of clocks. Before clocks guided satellites, they reorganized cities. For most of human history, local solar time was sufficient. Noon in one town occurred when the sun crossed that town's meridian. A town farther west reached noon slightly later. The difference might be a few minutes, and there was little reason to care. Travel was slow. Communities lived by local rhythms. Then railways compressed distance. A train leaving one city and arriving in another needed a timetable that passengers, stations, and railway employees could understand. If every town kept its own solar time, confusion followed. Telegraph networks made distant coordination even more immediate. A signal could cross a country faster than the sun appeared to move across it. Standard time zones were not discovered in nature. They were negotiated into existence because technology required shared schedules. The change was sometimes resisted. Local time felt natural. Standard time felt artificial, imposed by distant institutions and railway companies. Public clocks were adjusted. Noon separated from the local sun, entire regions agreed to behave as though one chosen meridian defined the hour for everyone. This is a useful distinction. Time as measured by physics is not the same as the conventions used to label it. The universe does not contain Monday, midnight, summertime, or any numbered year. These are human systems laid across astronomical and physical cycles. They are useful, often essential, but they should not be confused with the underlying structure. Even the line separating one calendar day from another is placed by agreement. Cross it, and the date changes, although nothing sudden happens to the ocean beneath. Clocks gradually became more regular as their moving parts improved. A famous story says that the young Galileo watched a lamp swing in the Cathedral of Pisa and timed its motion against his pulse. Whether every detail of the story is exact or not, Galileo did study pendulums and recognized that, for small swings, the period depends mainly on the length rather than the mass of the bob. A wide swing is not perfectly equal in timing to a narrow one, but the approximate regularity was remarkable. Christian Huygens built the first successful pendulum clock in the 17th century. The pendulum provided a repeating motion that could regulate gears far more accurately than many earlier mechanisms. Timekeeping improved from errors of many minutes per day toward errors measured in seconds. A pendulum clock turns gravity into rhythm. The bob accelerates downward, passes through its lowest point, rises, slows, and reverses. Energy moves between motion and gravitational potential. The escapement mechanism gives small pushes to replace energy lost through friction while allowing the gear train to advance one controlled step at a time. The clock's tick is not time itself. It is the sound of energy being released in measured portions. Pendulum clocks also revealed a subtle fact. The same clock can run at different rates in different locations. The strength of gravity varies slightly across Earth because of altitude, latitude, and local geology. A pendulum's period depends on gravitational acceleration. Move the clock, and its rhythm changes unless adjusted. Even before relativity, precision time was local. Mechanical clocks eventually gave way in many applications to quartz. Quartz crystals deform when voltage is applied and generate voltage when mechanically stressed. In an electronic circuit, a quartz crystal can vibrate at a highly stable frequency. Count the vibrations, and one can divide time far more accurately than with most ordinary gears. But quartz is still influenced by temperature, aging, and manufacturing differences. For the most precise standard, physicists turn to atoms. Atoms of the same isotope are identical in a way manufactured pendulums are not. A particular transition in cesium-133 has the same unperturbed frequency wherever the physical conditions are properly controlled. Since 1967, the SI second has been defined through exactly 9,192,631,770 periods of radiation associated with the transition between two hyperfine levels of the ground state of cesium-133. The number may sound arbitrary. It was chosen so the new atomic second would closely match the older astronomical second. The definition preserved continuity while replacing Earth's imperfect rotation with a quantum reference. Modern optical clocks use transitions at much higher frequencies in atoms or ions such as strontium, ytterbium, aluminum, and mercury. Higher frequency provides more cycles to count within the same duration, opening the possibility of still greater precision. Scientists are working toward a future redefinition of the second based on optical transitions, but the cesium definition remains the official one tonight. An atomic clock does not watch an atom ticking like a miniature pendulum. It uses an electromagnetic oscillator, measures how atoms respond, and continually corrects the oscillator toward the atomic resonance. The atoms provide the reference. the apparatus learns to follow it. Many clocks around the world contribute to International Atomic Time. Their readings are compared, weighted, corrected, and combined. Coordinated Universal Time, UTC, is built from atomic time but kept close to Earth's rotation through occasional adjustments such as leap seconds, though the future treatment of leap seconds is being changed by international agreement. The time shown on a network device is therefore not produced by one master clock sitting at the center of the world. It is the result of laboratories, radio links, fiber connections, satellites, algorithms, conventions, and relativity. Timekeeping has become a planetary collaboration. Atomic laboratories are not the only places where nature produces reliable rhythms. Some of the most remarkable clocks are collapsed stars turning in darkness. In 1967, Jocelyn Bell Burnell was a postgraduate student at Cambridge helping to study radio signals from the sky. The telescope she worked with did not produce elegant images. It covered long rolls of chart paper with ink traces, and the amount of paper was enormous. Bell Burnell learned the ordinary texture of interference, distant radio sources, and faults in the equipment closely enough to notice a small piece of signal she later described as a kind of scruff. It did not behave like the usual interference. It returned from the same region of sky. When the signal appeared clearly again, the pulses were separated by roughly 1 1/3 seconds. They were so regular that the team had to consider every explanation, including human transmitters, faulty electronics, satellites, and, half-jokingly, an intelligent source beyond Earth. The temporary label Little Green Men reflected the strangeness of the pattern, not a serious conclusion that aliens had been found. Then another pulsing source appeared in a different part of the sky, followed by others. A civilization was no longer a sensible explanation. Nature had made a new kind of clock. The sources were identified as neutron stars, the compact remnants left when massive stars collapse. A neutron star can contain more mass than the Sun compressed into a sphere roughly the size of a city. If its magnetic axis is tilted relative to its rotation axis, beams of radiation sweep through space. When one beam crosses Earth, a radio telescope receives a pulse, much as a distant lighthouse produces flashes. These objects became known as pulsars. Young pulsars can slow irregularly and sometimes experience sudden changes called glitches. But old millisecond pulsars have been spun up through interaction with companion stars and can rotate hundreds of times per second with extraordinary long-term stability. Their pulses do not arrive with the laboratory regularity of one perfect mechanical beat, because the signal crosses interstellar plasma. Earth moves, the pulsar moves, and space-time itself can disturb the path. Astronomers model all of those effects and predict the arrival times. A missing or early pulse is therefore not merely an error. It can be information. Pulsar timing has revealed planets around other stars, tested theories of gravity, measured the behavior of neutron stars, and created a possible method of navigation far from Earth. A spacecraft receiving signals from several known pulsars could compare their arrival times and estimate its position without relying entirely on instructions from home. Networks of millisecond pulsars can also act as a detector larger than the solar system. Gravitational waves passing between Earth and the pulsars slightly alter the timing pattern. The stars become distant reference clocks, and the space between them becomes part of the instrument. No pulsar replaces the best atomic time standards. Their strengths are different. Atomic clocks are built, controlled, and compared on Earth. Pulsars are spread across the galaxy and remain available wherever their beams can be detected. One measures time through quantum transitions in matter prepared inside a laboratory. The other measures it through the rotation of a dead star. The discovery began because one person examined miles of paper carefully enough to notice that a small irregular mark was regular. Time had written itself as a faint repeating signal from deep space. Not every natural clock repeats. Some clocks work by never returning to their earlier state. Radioactive atoms carry this kind of time. An unstable nucleus has a certain probability of decaying during any interval. No instrument can normally predict the exact moment when one particular atom will transform, but a large population follows an extraordinarily reliable statistical pattern. After one half-life, roughly half the original radioactive nuclei remain. After another, roughly half of those remain. The individual event is unpredictable. The collective rhythm is precise. This gave geology a clock that could run for millions or billions of years without gears, sunlight, or memory. Certain uranium isotopes decay through chains of transformations into stable isotopes of lead. Potassium-40 can become argon-40. Carbon-14 decays on a much shorter scale, useful for once-living material. Each system has a different range, set by its half-life and by the way atoms enter or leave a mineral, bone, shell, or piece of wood. The method is often summarized as reading a ratio between parent and daughter isotopes, but real dating is more careful. Scientists must know how the sample formed, whether it remained closed to the relevant elements, how contamination might have entered, and whether independent mineral systems agree. A number without geological context is not yet an age. When magma cools and a mineral crystal forms, the growing structure can accept some elements more easily than others. The crystal begins with a particular chemical state. Radioactive parents then decay at known rates while daughter products accumulate. The mineral becomes a sealed history, though heat, water, pressure, and later alteration can sometimes disturb the record. A rock does not know how old it is. Its atoms preserve relationships from which age can be inferred. For centuries, estimates of Earth's age were shaped by theology, sedimentation, erosion, ocean chemistry, and attempts to calculate how long the planet would take to cool. The answers varied wildly. Some estimates allowed only millions of years, creating tension with the long history required by geology and evolution. Radioactivity changed the available clock. In the middle of the 20th century, the problem reached a young geochemist named Claire Patterson. He wanted to determine the age of Earth using lead isotopes, especially the lead produced through the decay of uranium. But ordinary terrestrial rocks had been melted, recycled, weathered, and chemically altered throughout the planet's history. Earth had erased much of its own starting condition. Meteorites offered another route. They formed from the early solar system and preserved material from the same broad era in which Earth formed. By comparing lead isotope compositions in meteorites with lead in terrestrial materials, Patterson could reconstruct a much older clock. The work became unexpectedly difficult because lead was everywhere. Laboratory glassware, dust, reagents, pipes, paint, fuel residues, and the surrounding environment contaminated samples with amounts vastly larger than the ancient lead Patterson was trying to measure. Results refused to become clean and consistent. The problem was not the decay law. It was the modern world entering the experiment. Patterson responded by building one of the earliest ultra-clean laboratory environments for geochemistry. Surfaces were controlled. Reagents were purified repeatedly. Airborne particles were reduced. Procedures became almost ritualistically careful because a tiny, invisible contamination could overwrite billions of years of isotopic history. Precision required creating a room from which the present had been removed as completely as possible. In 1956, Patterson published an age for Earth of about 4.5 billion years. Modern estimates placed the planet near 4.54 billion years old. The exact value has been refined, but the basic scale established through meteorites and lead isotopes remains. Earth's age was not found by watching the planet from its beginning. It was reconstructed from transformations that had continued silently inside matter. The investigation also led Patterson toward another discovery. The abundance of lead contaminating his work was not natural background alone. Industrial lead had spread through air, oceans, ice, food, dust, and human bodies. The scientist trying to hear Earth's ancient clock found that modern pollution was shouting over it. He later became a determined opponent of environmental lead exposure. One effort to measure deep time became part of a struggle to change the present. Radioactive clocks now date volcanic eruptions, ancient minerals, archaeological remains, groundwater, planetary surfaces, and events in the evolution of life. Different isotopes cover different windows. Carbon-14 is useful across thousands to tens of thousands of years. Uranium lead systems can reach toward the formation of the solar system. These clocks do not tick in equal audible beats. They transform populations. They also reveal a subtle difference between age and duration. A crystal may have formed billions of years ago, been buried, heated, fractured, and exposed again. Several clocks inside it may have been partly reset at different moments. One mineral can preserve the age of crystallization, while another records later metamorphism. Stone can contain more than one past. The same principle appears in the body. Carbon atoms enter through food, chemical elements move through tissue, and radioactive isotopes decay whether or not anyone observes them. Matter carries temporal information through irreversible change. A half-life does not tell one atom when to decay. It tells a population how to fade. Once again, time appears through probability, comparison, and records left by change. This precision created a question that ordinary clocks had hidden. If two perfect clocks are separated and later compared, must they always agree? Classical intuition says yes. If both are functioning correctly, time should pass at one universal rate. A clock may be damaged, slowed by friction, or set incorrectly, but time itself should be the same everywhere. Isaac Newton described absolute, true, and mathematical time as flowing equably without relation to anything external. In this picture, the universe has one invisible cosmic clock. Events happen at positions in space and moments in time. Observers may measure badly, but there is a correct universal answer beneath their errors. This framework worked brilliantly for ordinary motion. It still works as an excellent approximation for most daily life. A train timetable does not need quantum gravity. A falling cup can be described without worrying that simultaneity is relative. But light created trouble. 19th century physics understood waves through media. Sound traveled through air. Water waves traveled across water. It therefore seemed natural that light must travel through something too, an invisible substance filling all space. Physicists called it the luminiferous ether. Earth should move through this ether as it traveled around the sun. If so, a laboratory on Earth ought to feel an ether wind. Light sent in the direction of Earth's motion should take a slightly different time from light sent across that motion, just as a swimmer takes different times moving with, against, or across a current. Albert Michelson designed an interferometer sensitive enough to compare the journeys. A beam of light was split into two perpendicular paths, reflected by mirrors, and recombined. If one beam had taken slightly longer, the returning waves would shift their interference pattern. In 1887, Michelson and Edward Morley performed the most famous version of the experiment in Cleveland. To reduce vibration, the apparatus rested on a massive stone slab floating in mercury, allowing the entire instrument to rotate. They expected the fringe pattern to change as the arms turned relative to Earth's presumed motion through the ether. The expected shift did not appear. Michelson and Morley did not walk away announcing that space and time had been overturned. They regarded the result as deeply disappointing, and many physicists tried to preserve the ether. George Fitzgerald and Hendrik Lorentz proposed that motion through the ether might physically contract objects along their direction of travel, hiding the expected difference. Lorentz developed transformations that mixed measured lengths and times in precisely the mathematical way later required by relativity. The old framework was bending to protect itself. Einstein took a different route. Working in the Swiss Patent Office, he examined inventions involving electrical signals, synchronization, and moving machinery, while pursuing theoretical physics outside his official duties. Historians still debate how strongly the Michelson-Morley experiment influenced his reasoning, and his 1905 paper did not present the theory as a simple conclusion from that one result. He began instead with principles. The laws of physics should have the same form for all inertial observers, and light in vacuum should have the same measured speed for each of them. There would be no privileged observer resting inside an invisible ether and no experiment revealing absolute uniform motion. If those principles were correct, the problem was not that clocks and rulers were being distorted away from their true values. Their readings were the physical values available to each observer. Space and time themselves had to fit together differently. To preserve the speed of light, observers moving relative to one another must disagree about lengths, durations, and which distant events occur simultaneously. The result was special relativity, published in 1905. A failed search for an invisible wind had helped clear the way for a universe without absolute rest. One of Einstein's most powerful moves was to question simultaneity. What does it mean to say that two distant events happen at the same time? Near one location, the question seems easy. Compare both events with one clock. At great distances, signals must travel between the events and observer. Light takes time. To synchronize distant clocks, one must establish a procedure, usually involving exchanged light signals and assumptions about their travel. Einstein imagined clocks placed throughout space and synchronized using light. But observers moving relative to one another do not agree on which distant events are simultaneous. Consider a long train moving along a track. Lightning strikes the front and rear of the train. An observer standing midway beside the track may receive both flashes together and conclude that the strikes were simultaneous. A passenger sitting at the middle of the moving train travels toward the flash from the front and away from the flash from the rear. Because light travels at the same speed relative to the passenger receives the front flash first and concludes that the front strike happened earlier. Neither observer is mistaken. Their disagreement is not caused by slow brains or defective clocks. Simultaneity at separated locations depends on the observer's state of motion. There is no universal present shared by all observers. This is one of the deepest changes in human thinking about time. The word now feels absolute because nearby events and ordinary speeds make the differences too small to notice. But across large distances and high relative velocities, different observers slice space-time into past, present, and future differently. The universe does not provide one preferred way to divide all events into simultaneous layers. Time dilation follows from the same structure. Imagine a simple clock made from two mirrors facing each other, with a pulse of light bouncing between them. Each round trip is one tick. For an observer moving with the clock, the light travels straight up and down. For an observer watching the clock pass sideways, the light follows a diagonal path because the mirrors move while the pulse travels. The diagonal path is longer. Since both observers measure the same speed of light, the moving clock must take more time between ticks. From the stationary observer's perspective, the moving clock runs slowly. This is not an illusion caused by seeing delayed light. After correcting for signal travel, the difference remains. It applies not only to clocks, but to physical processes. Unstable particles live longer when moving rapidly relative to the laboratory. Biological aging, chemical reactions, and mechanical motion all follow the proper time along their path through space-time. The effect is tiny at familiar speeds. A person on a bicycle experiences a difference far too small to feel. At speeds close to light, it becomes dramatic. Cosmic ray particles called muons are created high in Earth's atmosphere. At rest, they decay so quickly that many should not survive long enough to reach the ground. But they move at speeds close to light. In Earth's frame, their internal processes are time-dilated, allowing large numbers to reach detectors at the surface. In the muon's frame, the distance through the atmosphere is length-contracted. Both descriptions agree on the observed result. Nature performs the relativity experiment continuously above us. The traveling twin story makes the effect personal. One twin remains on Earth. The other accelerates into space, travels at high speed, turns around, and returns. The traveling twin has experienced less proper time and is younger at reunion. This is sometimes called a paradox because each twin can initially describe the other's moving clock as slow, but their journeys through space-time are not symmetric. The traveling twin changes inertial frames during departure, turnaround, and return, while the Earth twin follows a different path. Proper time depends on the entire path through space-time. In ordinary geometry, the straight path between 2 points is the shortest distance. In the space-time geometry of special relativity, the inertial path between suitable events can have the greatest proper time. Different routes between the same departure and reunion can contain different amounts of aging. A life becomes a world line. This language does not mean life is predetermined. A world line is simply the path an object traces through space-time. Every heartbeat, step, and decision occurs along it. Proper time is what an ideal clock traveling beside the object measures. The word proper here does not mean morally correct. It means local to that path. Special relativity joins space and time into space-time. Hermann Minkowski, one of Einstein's former teachers, developed the geometric formulation and famously said that space by itself and time by itself were destined to fade into shadows, while only a union of the two would preserve an independent reality. Different observers disagree about spatial distances and time intervals, but they agree on the space-time interval, a combination of space and time that remains invariant. This is similar to observers rotating ordinary coordinates. One person may describe a line as extending mostly east-west. Another using rotated axes may describe part of it as north-south. They disagree about the components but agree on the line's length. In relativity, observers moving differently disagree about how much separation belongs to space and how much belongs to time. The invariant space-time interval plays the role of the shared geometry. Time became less like a river flowing outside the universe and more like a dimension woven into the relationships among events. Then gravity changed it again. Einstein's general theory of relativity, completed in 1915, describes gravity not as an ordinary force pulling across fixed space, but as the curvature of space-time produced by matter and energy. Objects moving freely follow the straightest available paths through curved space-time. A planet orbits not because an invisible string drags it around the sun, but because the geometry through which it moves is curved by the sun's mass. Time is part of that geometry. Clocks at different gravitational potentials tick at different rates. Closer to a massive body, a clock runs more slowly relative to a clock farther away. This statement must always be handled carefully because each local observer experiences their own clock as normal. A heartbeat beside the clock does not feel stretched. The difference appears when clocks following different paths or residing at different gravitational levels are compared. Even across the height of a room, the effect exists. A clock on a shelf ticks very slightly faster than a clock on the floor because it is higher in Earth's gravitational field. Modern optical clocks have measured gravitational time dilation across height differences as small as about a millimeter. The difference is extraordinarily tiny, but it is real. Your head ages at a slightly different rate from your feet while you stand. The accumulated difference across a human life is far too small to matter biologically, yet the principle reaches from the body to the architecture of the cosmos. There is no single rate at which time passes everywhere. Rate depends on motion and gravity. In the 1970s, Joseph Haffel and Richard Keating carried atomic clocks aboard commercial aircraft flying eastward and westward around the world. The clocks were later compared with reference clocks that had remained at the United States Naval Observatory. Speed and gravitational altitude affected them in opposite ways depending on the journey. Within experimental uncertainty, the measured differences agreed with relativity. Time had been carried around Earth and returned changed. Today, the effect is part of daily technology. GPS satellites orbit high above Earth while moving rapidly relative to users on the ground. Special relativity makes their moving clocks run slower. General relativity makes their clocks run faster because gravity is weaker at their altitude. The gravitational effect is larger, producing a net gain of about 38 microseconds per day relative to clocks on Earth's surface. 38 microseconds sounds insignificant, but light travels more than 11 kilometers in that interval. Without relativistic corrections, positioning errors would grow rapidly. Every accurate blue dot on a map quietly confirms that time is not universal. Gravity can also turn clocks into sensors. Because clock rates depend on gravitational potential, sufficiently precise clocks can measure height differences and changes in Earth's gravitational field. A future network of optical clocks could help map underground structures, monitor shifts in water or ice, improve geodesy, and test fundamental physics. The clock becomes a probe of curved spacetime. Near a black hole, gravitational time dilation becomes extreme. A distant observer watching a clock fall toward the event horizon receives signals that are increasingly delayed and redshifted. The falling clock appears to slow and fade. From the viewpoint of the falling traveler, however, their own clock continues normally, and in a sufficiently large black hole, they may cross the horizon without encountering a locally marked boundary at that instant. The two descriptions refer to different ways of assigning coordinates and receiving information. The event horizon is not a material surface where time physically stops for the traveler. It is a causal boundary beyond which signals cannot return to the distant universe. Popular descriptions sometimes say that an astronaut sees the entire future of the universe while falling into a black hole. That is not generally correct. The relationship among signals, horizons, and finite survival time is more constrained. Relativity allows dramatic differences in elapsed time, but not an unlimited cinematic view of all future history for an ordinary falling observer. Still, black holes make the relativity of time impossible to ignore. Imagine two clocks. One remains far from the black hole. The other spends time deeper in the gravitational field and later returns, if the path is physically possible. The returning clock records less elapsed time. Its owner has traveled into the future relative to the distant observer. This is not science fiction time travel into the past. It is the same one-way time travel produced by high speed or gravitational differences. Everyone moves into the future, but relativity allows different routes to contain different durations. The future can be reached unevenly. At this point, the original question becomes more complicated. Is time real? Clocks disagree, but they disagree according to exact laws. Proper time is measurable. Relativistic differences change particle decay, satellite navigation, and aging. Whatever time is, it is not merely an arbitrary human illusion. Yet the universal flowing time imagined by Newton is not part of relativity. There is no cosmic master clock and no observer-independent global now in ordinary spacetime. Something real has survived, but it is not the thing common sense first expected. The next question is why time seems to have a direction at all. The equations of classical mechanics can usually run forward or backward. If a film shows two ideal billiard balls colliding, the reversed film may also show a physically possible collision. Maxwell's equations for electromagnetism, in their basic form, do not strongly prefer one-time direction. Much of quantum mechanics evolves through equations that are reversible in time, with important subtleties involving measurement and particular symmetry violations. But daily life is filled with irreversible events. Cream mixes into coffee and does not separate. Heat flows from a warm cup into a cool room. A perfume molecule spreads through the air and does not gather itself back into the bottle. A person remembers childhood but not tomorrow. A glass shatters and remains broken. The laws governing the particles may permit reversal, yet the world of many particles has an arrow. The bridge between these levels is entropy. Entropy is one of the most important and most misunderstood ideas in science. It is often described simply as disorder, but that word can create as much confusion as understanding. A messy bedroom may look disordered, yet thermodynamic entropy has a precise statistical meaning. It is related to the number of microscopic arrangements compatible with what we observe at the larger scale. Imagine a box divided into two halves. All the gas molecules begin on the left. Remove the divider, and the molecules spread throughout the box. Nothing in the microscopic laws forbids them from moving back into the left half. Each collision can be reversed in principle, but there are vastly more ways for the molecules to be distributed across the full box than for every molecule to occupy one half. The spread-out state is not preferred because the molecules know where they should go. It is preferred because almost every possible microscopic arrangement looks spread out at the large scale. Entropy measures this abundance of possibilities. Ludwig Boltzmann spent much of the 19th century building the statistical bridge between moving particles and thermodynamics. Temperature, pressure, and entropy could be understood as collective properties emerging from enormous numbers of molecules. On his gravestone appears the equation connecting entropy with the logarithm of the number of microscopic states compatible with a macroscopic condition. The logarithm matters because it makes the entropy of independent systems add, but the deeper idea is simple. A high entropy condition can be realized in overwhelmingly many microscopic ways. A low entropy condition is special. An intact glass standing at the edge of a table is a highly organized arrangement. After it falls, energy spreads into sound, heat, motion, and countless fractures. There are enormously many ways for the pieces, vibrations, and surrounding molecules to share that energy. There are extraordinarily few ways for all those motions to coordinate, so the fragments rise, rejoin, cool the floor, absorb sound from the air, and return the glass to the table. The reversed event is not strictly forbidden by the ordinary microscopic equations. It is fantastically improbable. This is the statistical arrow of time. The second law of thermodynamics says that the entropy of an isolated system tends not to decrease. The word tends is important at microscopic scales, where fluctuations can produce brief local decreases. But for a macroscopic system containing unimaginable numbers of particles, a large spontaneous reversal is so improbable that it will not occur within any meaningful duration. A spoonful of cream contains roughly more molecules than a human mind can picture. Once those molecules are mixed through coffee, asking them all to reverse their velocities in exactly the coordinated way required for separation is not like asking for an unlikely card draw. It is asking for a coincidence with a probability buried under an astronomical tower of numbers. The arrow is therefore robust, even though it emerges from laws that are often nearly reversible. James Clerk Maxwell once imagined a tiny intelligent being controlling a door between two gas chambers. The being, later called Maxwell's demon, allows fast molecules to pass one way and slow molecules the other, apparently creating a temperature difference without doing work and violating the second law. The thought experiment forced physicists to examine the relationship among entropy, information, and measurement. The demon must observe molecules, store information, make decisions, and eventually erase or reset memory. When the full physical cost of information processing is included, the apparent violation disappears. Information is not outside thermodynamics. A memory must be embodied in a physical system. This connection reaches into every computer. Erasing information has a minimum thermodynamic cost under ideal conditions, known through Landauer's principle. Real computers dissipate far more energy than this minimum, but the principle shows that logical operations are connected to heat and entropy. Even a thought leaves a physical trace. The brain consumes energy, changes synapses, moves ions, releases neurotransmitters, and produces heat. Remembering the past is not a view into an abstract archive detached from matter. It is the activation of a physical structure created through previous interactions. This helps explain why the psychological arrow of time points in the same direction as the thermodynamic arrow. We remember lower entropy past conditions because records are formed through irreversible processes. Light from an event reaches a camera. Chemical changes fix an image. Sound moves a microphone. Neural activity changes connections. A footprint compresses sand. Tree rings form. Fossils mineralize. Each record involves energy dispersal and entropy increase in a wider environment. The past leaves traces because events create records as entropy grows. The future has not left records in the present in the same way. We can predict it, imagine it, fear it, or plan for it, but we do not possess physical memories produced by events that have not yet occurred along our world line. This asymmetry can make time feel as though it flows from a remembered past toward an unknown future. Yet physics may describe the situation differently. Perhaps the flow is not a property added to the universe. Perhaps it is the experience of a memory-forming system moving along an entropy gradient. To understand that possibility, it helps to return to the beginning of the universe. If entropy tends to increase, then the earlier universe must have had lower entropy than the later universe. The deepest mystery of the arrow of time is not simply why disorder grows. Statistical mechanics explains why systems move from special states toward more typical ones. The deeper mystery is why the universe began in such a special state at all. The early universe was hot, dense, and nearly uniform. At first glance, this may sound like maximum disorder. For a gas without gravity, uniform spreading can indeed correspond to high entropy. But gravity changes the story. Matter under gravity tends to clump. A smooth distribution can evolve into stars, galaxies, black holes, and complex structure. Black holes carry enormous entropy. From a gravitational perspective, the early universe's remarkable smoothness represented a low entropy condition. The universe began with room for entropy to grow. As it expanded, tiny density variations were amplified by gravity. Matter gathered. Stars formed. Nuclear reactions produced heavier elements. Planets condensed. Energy flowed from hot stars into colder space. On at least one planet, these gradients helped support chemistry, metabolism, evolution, and minds capable of wondering why time has a direction. Life does not violate the second law. Living systems create local order by consuming free energy and increasing entropy in their surroundings. A plant uses sunlight to build complex molecules while releasing heat. An animal eats organized chemical energy, maintains tissues, moves, thinks, and exports waste and heat. A refrigerator creates a cold, ordered interior by releasing more heat into the room. Local organization is possible because the larger system pays the thermodynamic cost. The body resting tonight is highly structured, but it is not isolated. It breathes, radiates heat, exchanges matter, and uses stored energy. Its order is maintained through continuous flow. Life is a temporary pattern held away from equilibrium. Equilibrium is the condition in which useful differences have faded. Temperatures equalize. Pressures balance. Chemical gradients disappear. Nothing prevents microscopic motion, but there is no remaining large-scale gradient from which organized work can easily be extracted. A living body depends on differences. Oxygen high in the lungs and lower in tissues, sodium concentrated outside cells, and potassium inside. Chemical energy stored in molecules, electrical potentials across membranes, temperature differences between body and environment. The body is not calm because nothing changes. It is calm because countless changes are regulated. Time's arrow is written through these gradients. Metabolism consumes them. Aging accumulates transformations that cannot be perfectly reversed. Repair restores local structure but releases heat. Sleep reorganizes memories and maintains tissue while the larger thermodynamic account continues forward. The connection between entropy and aging is not simple enough to say that aging is merely entropy. Organisms have repair systems, and biological aging involves genetics, metabolism, cellular damage, regulation, inflammation, and evolutionary trade-offs. Still, no organism escapes the broader thermodynamic direction. Maintenance requires energy. Repair is never perfectly complete. The body can resist local disorder for decades, but only by participating in the larger increase. The arrow also appears in radiation. A stone dropped into water creates outgoing ripples. We do not normally see waves arriving from every direction and converging perfectly to launch the stone upward. Maxwell's equations can describe advanced as well as retarded solutions in mathematical contexts. Yet nature overwhelmingly presents radiation spreading outward from sources. This may again reflect boundary conditions. The universe contains records of outgoing radiation from past sources, not exquisitely arranged incoming waves prepared from the future. Cause comes before effect in ordinary experience. A match is struck, then a flame appears. A bell is hit, then sound spreads. A decision is made, then a hand moves. Relativity complicates the word before for distant events, but it preserves causal order for events that can influence one another. If a signal traveling at or below light speed can connect two events, all observers agree on which event could be the cause and which the effect. Their measured time intervals may differ, but causal structure remains. Space-time can be divided by light cones. At any event, the future light cone contains events that can be influenced by signals traveling no faster than light. The past light cone contains events that could have influenced the present event. Events outside both cones are space-like separated. Their time order can differ between observers, but they cannot exchange ordinary causal signals without exceeding light speed. The relativity of simultaneity does not mean everything can happen in any order. It means nature protects causality through geometry rather than through one universal clock. This geometry invites a startling interpretation called the block universe. In a block view, space-time is a four-dimensional whole containing events we call past, present, and future. A person's birth, tonight's room, and a distant future event occupy different regions of space-time, just as different cities occupy different locations in space. The present does not sweep through the block as an objective universal surface. Instead, each observer has a local experience along a world line. Relativity encourages this view because there is no observer-independent global now. If distant simultaneity changes with motion, it becomes difficult to argue that one unique set of events exists while all others are unreal. A mountain does not disappear because someone is not standing beside it. In the block view, an event does not become unreal because it lies earlier or later along a world line. This idea can feel unsettling. If future events already belong to space-time, is everything fixed? Does choice disappear? Physics does not settle the philosophical question so easily. A block description represents the total pattern of events. It does not necessarily explain why the pattern has the details it does, how agency should be understood, or whether indeterministic quantum events are included as branches, probabilities, or definite outcomes. A map of a path does not make the traveler's decisions unreal, but a complete map extending into the future would raise deeper questions about what a decision means. Some philosophers and physicists prefer presentism, the view that only the present is real. The past no longer exists, and the future does not yet exist. This matches ordinary experience, but faces difficulty in relativity because different observers disagree about distant simultaneity. Which present is the real one? One response is to seek a preferred foliation of space-time, a hidden way of slicing it into universal moments. Standard relativity does not require such a structure, although some theories or cosmological models may provide useful preferred frames in particular contexts. Another view, sometimes called the growing block, holds that the past and present exist while the future is added as events occur. The block grows. This preserves an objective becoming but must explain where the growing edge lies in a relativistic universe. There is also the moving spotlight view, in which all events exist, but one layer is objectively illuminated as present. Relativity again makes the universal spotlight difficult to define. No philosophical picture has one universal agreement. This disagreement reveals that equations and experience answer different questions. Relativity tells us how clocks compare, how causal order works, and how space-time geometry behaves. It may favor some metaphysical interpretations over others, but it does not place a label inside the equations saying which events truly exist. The feeling of passage remains. You do not experience your life as a four-dimensional diagram. You experience one moment replacing another. The sound of this sentence exists, fades, and becomes memory. The next sentence is anticipated but not yet heard. Where does that experience come from? The brain does not contain one central clock producing a perfect internal timeline. Time perception is distributed across many systems. Different neural circuits estimate intervals, sequence events, predict rhythms, and connect memory with expectation. The suprachiasmatic nucleus in the hypothalamus coordinates circadian rhythms near 24 hours. It receives light information from the eyes and helps synchronize sleep, temperature, hormone release, metabolism, and behavior with day and night. Yet this biological clock does not count seconds in conscious experience. Short intervals involve other networks, including the basal ganglia, cerebellum, supplementary motor areas, prefrontal cortex, sensory systems, and structures involved in attention and memory. The brain may use changing patterns of activity, oscillations, accumulation processes, prediction, and contextual cues rather than one universal neural stopwatch. This is why subjective time is elastic. An hour waiting without stimulation can feel long. An hour absorbed in an engaging activity can disappear. A frightening event may seem to slow, although experiments suggest that the richer memory formed during intense attention can contribute to the later impression that more time passed. Novel experiences create dense records. Routine periods can compress in memory because fewer distinctive events separate them. A childhood summer may seem enormous because it contained novelty and represented a large fraction of the life already lived. A year in adulthood may feel shorter because it is compared with many previous years and may contain repeated routines. The clock has not changed. The architecture of memory has. Attention also changes duration estimates. When a person watches time closely, more mental resources are devoted to tracking it, and intervals often feel longer. When attention is absorbed elsewhere, fewer temporal cues are counted. Pain can lengthen time. Boredom can lengthen time. Anxiety can make the future feel close and urgent while individual minutes crawl. Depression can alter temporal experience. Certain neurological conditions and drugs can distort timing. The present perceived by the brain is not an infinitely thin mathematical instant. Sensory signals arrive at different speeds. Light, sound, touch, and internal body signals require different processing times. The brain integrates information across short windows to create a coherent moment. When watching someone speak from a small distance, the sound reaches the ears slightly after the light reaches the eyes, yet the events are usually perceived together. The brain tolerates and corrects small timing differences. At greater distances, as with fireworks, the separation becomes too large and the illusion breaks. Conscious now is constructed. Vision itself is delayed by neural processing. By the time an event becomes consciously visible, it has already happened. The brain compensates through prediction, especially during movement. A ball can be caught because the nervous system estimates where it will be, not because consciousness waits passively for old images. The experienced present, therefore, contains a mixture of recent sensory evidence and prediction. Music reveals this beautifully. A melody does not exist in one instant. Each note becomes meaningful because previous notes remain in short-term memory while the brain anticipates what may follow. Rhythm depends on intervals. Harmony unfolds. If consciousness were confined to a durationless point with no retention, music would dissolve into unrelated sounds. The mind holds a small temporal window. Language does the same. The meaning of this sentence depends on words that have already vanished acoustically. Memory preserves them long enough for structure to emerge. The sentence exists for experience as an organized span, not as one isolated instant. William James called the brief duration held in awareness the specious present. It is not false in the sense of being useless. It is the practical present through which experience becomes continuous. Different creatures may inhabit different temporal worlds. Small animals often process visual changes more rapidly than large animals, and some species can resolve flickering that humans perceive as steady light. A fly may respond to movement with speed that makes human action seem slow. A tortoise, bird, dog, and human do not necessarily divide experience into the same perceptual frames. Metabolism, nervous system speed, sensory ecology, and behavior shape temporal resolution. Plants keep time too. Leaves open and close. Flowers release scents at particular hours. Genes cycle in activity. Even in constant darkness, circadian rhythms can continue for a while because internal molecular feedback loops generate approximately daily oscillations. In fruit flies, research on genes and proteins such as period and timeless helped reveal the molecular machinery of circadian clocks. Similar principles appear across many organisms. Clock genes produce proteins that eventually inhibit their own production, creating delayed feedback cycles. Light and other signals adjust the rhythm to the environment. The biological clock is not a tiny watch hidden in a cell. It is chemistry chasing its own tail. Human circadian rhythms also rely on molecular feedback loops in cells throughout the body. The central clock coordinates peripheral clocks in liver, muscle, fat, pancreas, and immune tissues. Food timing, activity, temperature, and hormones can shift these local rhythms. Jet lag occurs because the environment changes faster than the clocks can adjust. The wall clock at the destination announces morning, while cells may still expect night. Sleep, digestion, alertness, and hormone release become temporarily misaligned. The experience is a reminder that social time and biological time can disagree. Daylight saving changes, night shifts, artificial light, and irregular schedules create smaller versions of the same conflict. Electric lighting extended activity beyond sunset, but the body still carries rhythms shaped by the rotation of Earth. Time is written into physiology because the planet turns. There are also developmental clocks. Embryos build tissues and sequences. Puberty changes the body over years. Cells count divisions, respond to signals, and move through cycles of growth and rest. The immune system changes with age. Bones remodel. Hormone patterns shift. A body is not merely located in time. It is made by timing. Consider the heartbeat. Each cardiac cell contains ion channels that open and close in sequence. Pacemaker cells generate rhythmic electrical changes. The heart speeds during exertion, slows in sleep, and varies slightly from beat to beat. Perfect mechanical regularity would not necessarily indicate health. Flexibility allows adaptation. Breathing has rhythm. Walking has rhythm. Speech has rhythm. Neural oscillations coordinate activity across the brain. The body is an orchestra of clocks that rarely share one exact period, yet remain sufficiently coordinated for life. If every process had to wait for one central command, the system would be too slow. Timing is distributed. This returns us to the question of whether time is one thing. The second used by an atomic clock, the circadian day, the felt length of a memory, and the thermodynamic arrow are connected but not identical. A person can feel that time has stopped while an atomic clock continues. A satellite clock can disagree with a ground clock while both bodies follow normal biological rhythms locally. Entropy can increase during an interval that feels brief or long. Time measured, time directed, and time experienced are different layers. The geological world adds another layer: deep time. Human intuition evolved among days, seasons, generations, and lifetimes. 1,000 years is difficult to feel. 1,000,000 years becomes almost abstract. Earth's history extends across about 4.5 billion years. The universe has expanded for about 13.8 billion years. Numbers this large often flatten into the same vague idea of very long ago. Geology had to teach the mind new scales. Rock layers preserve sequences. Sediments accumulate. Volcanoes deposit ash. Rivers cut valleys. Mountains rise and erode. Radioactive isotopes decay at measurable rates. Fossils appear and vanish in ordered strata. The planet contains clocks that do not look like clocks. Radiometric dating compares parent and daughter isotopes. A radioactive isotope decays with a characteristic half-life, meaning that over a given interval, half of a large population is expected to transform. Individual atoms decay unpredictably, but large populations follow stable statistical curves. The same quantum randomness that makes one decay time uncertain makes geological dating reliable in aggregate. Tree rings count years. Ice layers trap ancient atmospheres. Coral growth bands record seasons. Orbital cycles leave patterns in sediments. The past survives as structure. Deep time is reconstructed from records created by irreversible processes. The age of a rock is not written as a date on its surface. It is inferred from present conditions through laws believed to have remained stable. Science turns matter into memory. Starlight is another form of memory. Looking at the moon means seeing it roughly a second in the past. Sunlight is about 8 minutes old when it reaches Earth. Light from nearby stars may have traveled years. Light from distant galaxies has traveled millions or billions of years. Astronomy never sees the remote universe exactly as it is now. It sees layers of the past arranged by distance. There is no way to correct this delay and view a distant galaxy's present immediately. Its current state may be outside our past light cone. The information has not had time to arrive. The night sky is a map of different times. Some stars visible tonight may already have changed or died, while their older light continues across space. This is not because the stars are unreal. It is because information travels at a finite speed, and the word now cannot simply stretch across the cosmos. The farther we look, the earlier we see. Telescopes become time machines in one direction. They receive ancient light. The cosmic microwave background carries information from a time when the universe had cooled enough for light to travel freely, about hundreds of thousands of years after the hot early phase. Before that, the universe was opaque to ordinary light. Other messengers, such as neutrinos or gravitational waves, may reveal earlier epochs, though they are extraordinarily difficult to detect. Cosmology builds history from signals reaching one present location. The age of the universe itself depends on cosmological models, observations of expansion, the cosmic microwave background, element abundances, and other evidence. In general relativity, different cosmological observers can use a natural cosmic time associated with the large-scale expansion when the universe is sufficiently homogeneous. This provides a useful shared age for the cosmos, even though relativity denies a universal time in every possible spacetime. The universe can possess a practical cosmic clock without restoring Newton's absolute time. Expansion gives another meaning to duration. Galaxies separate as space evolves on large scales. Light stretches to longer wavelengths. Stars form and die. Black holes grow. Entropy increases. Far in the future, if current cosmic acceleration continues, distant galaxies outside our gravitational neighborhood will recede beyond observable reach. Stars will exhaust fuel. Matter may decay if protons are unstable, though this has not been observed. Black holes may evaporate through Hawking radiation over fantastically long intervals. The future of time becomes entangled with the future of usable change. If the universe approaches a state of maximum entropy, sometimes called heat death, large-scale gradients will fade. Events may still occur for immense durations, but the capacity for complex work diminishes. A clock requires a process. A memory requires change. In a perfectly featureless equilibrium, the distinction between one empty interval and another becomes operationally difficult. Would time still exist if nothing changed? Newton would have said yes. Absolute time continues even in an empty universe. Relational thinkers such as Leibniz argued that time is the order of events, not an independent container. If nothing changes, there is no fact about how much time has passed except through hypothetical relations. The debate remains alive in modern form. Relativity gives space-time geometric reality. Gravitational waves carry energy. Curvature influences motion. Empty space-time can have structure. Yet measurements of time still require physical clocks, and clocks require change. Perhaps time exists as geometry even when no clock ticks. Perhaps the concept becomes meaningful only through relationships. Physics offers reasons for both intuitions, depending on the level being described. Quantum mechanics treats time differently from position. In ordinary non-relativistic quantum theory, the state of a system evolves with a time parameter. Position is represented by an operator whose possible measured values belong to the quantum state. Time usually appears outside the state as the parameter telling the equation how the state changes. The Schrödinger equation is an equation of evolution. Give it a wave function at one time, and it predicts the wave function at another. The equation is deterministic between measurements, even though particular measurement outcomes are probabilistic. Time stands in the background, quietly organizing quantum change. This creates tension with general relativity. In relativity, space-time is not a fixed stage. Its geometry responds to matter and energy. Time is part of a dynamical field. In standard quantum mechanics, time is often treated as an external parameter supplied before the experiment begins. A theory of quantum gravity must somehow combine these roles. The problem becomes sharp in attempts to describe the entire universe quantum mechanically. There is no external laboratory clock outside the universe. Every clock is part of the system being described. In canonical approaches to quantum gravity, one encounters the Wheeler-DeWitt equation. In a simplified description, it resembles a quantum equation for the state of the universe, but it does not contain an ordinary external time parameter. The universe appears frozen in the equation. This is called part of the problem of time. The word frozen can be misleading. The equation does not necessarily say that nothing happens in experience. It says that the familiar external time used in ordinary quantum mechanics may not be fundamental at this level. Change may have to be described relationally. One part of the universe can serve as a clock for another. Imagine two quantum systems correlated with each other. Instead of asking how system A changes relative to an external time, one asks what state A has when system B shows a particular clock reading. The total state may be stationary in a formal sense, while internal observers experience correlations that look like evolution. Time can emerge from relationships inside a timeless whole. This idea appears in several forms, including relational approaches and the Page-Wouters mechanism. None has settled the full problem of quantum gravity, but they demonstrate that apparent evolution does not logically require an external cosmic clock. A film reel provides a limited analogy. The entire reel can exist at once, containing every frame. A character within the sequence experiences events in order because each frame contains records of earlier frames and conditions leading toward later ones. The reel does not need an external spotlight moving across it for the sequence to have structure. But the analogy is incomplete. A film reel is itself an object in time, while the universe cannot be placed on a table outside itself. Quantum correlations are not photographic frames. The point is only that order and internal change may emerge without fundamental flow. Some physicists suspect that time, like temperature, is emergent. Temperature feels fundamental because warm and cold are immediate experiences. Yet a single isolated particle does not have temperature in the usual thermodynamic sense. Temperature emerges from the statistical behavior of many degrees of freedom. Perhaps time also emerges when many quantum relationships are viewed at a larger scale. In some approaches, space-time may arise from patterns of quantum entanglement. In others, causal relations among events are more fundamental than smooth geometry. Loop quantum gravity explores discrete quantum states of geometry. String theory describes fundamental extended objects and includes gravity through quantum excitations. Causal set theory begins with a discrete order of events. Other proposals treat space-time as information, networks, condensates, or collective behavior. These ideas are not experimentally confirmed final answers. They are attempts to reach a regime where current theories no longer fit comfortably together. The Planck time, about 5.4 times 10 to the power of minus 44 seconds, is often mentioned as the scale at which quantum gravitational effects may become unavoidable. It is derived from fundamental constants associated with gravity, quantum mechanics, and light. The Planck time is not necessarily the smallest possible tick of reality. Physics does not yet know whether time is discrete. It is the time light takes to travel one Planck length in vacuum, and it marks a scale where familiar descriptions are expected to require deeper theory. To compare it with 1 second is almost impossible intuitively. There are more Planck times in a second than there have been seconds in the age of the universe by an enormous margin. If time is granular, the grains would lie far beyond direct, ordinary measurement. If time is continuous, the Planck scale may still mark a change in how geometry behaves. Quantum clocks also face limits. A clock is a physical system. To resolve shorter intervals, it needs sufficiently rapid, distinguishable changes. Energy, size, stability, gravitational influence, and quantum uncertainty all matter. Concentrate too much energy into too small a region, and gravity becomes important. Try to isolate a clock perfectly, and it cannot communicate its reading. Couple it strongly to the world, and noise disturbs it. There is no clock outside physics. This sounds obvious, but it changes the philosophical problem. Time is not measured by an ideal observer untouched by the universe. Every measurement occurs through matter, fields, energy, signals, and causal delay. Even atomic clocks do not reveal one hidden stream. They compare carefully controlled quantum transitions along particular world lines. Quantum mechanics also raises questions about the arrow of time through measurement. The Schrödinger equation is usually reversible. A quantum state evolves unitarily, preserving information. Yet a measurement appears to produce one definite outcome from several possibilities. In traditional textbook language, the wave function collapses, and collapse seems irreversible. Different interpretations handle this differently. In many worlds approaches, there is no fundamental collapse. The measuring system becomes entangled with the observed system, and decoherence prevents branches from interfering in ordinary conditions. The underlying evolution remains reversible, while observers within branches experience definite records and an arrow connected to low entropy conditions. Objective collapse theories add genuine irreversible processes to the dynamics. Copenhagen-style interpretations treat measurement outcomes as fundamental features of experimental description. Relational and information-centered interpretations frame the transition in other ways. No interpretation has resolved every question to universal satisfaction. Decoherence is essential, but does not by itself explain the origin of time's arrow. Interaction with the environment spreads phase information into many degrees of freedom, making interference between macroscopic alternatives effectively inaccessible. But the equations allowing this spread are still reversible. The asymmetry depends on the environment beginning in a special, relatively uncorrelated condition. Again, the low entropy past enters the story. The quantum arrow and thermodynamic arrow appear to align because measurements, records, observers, and environments all develop within a universe that began in a special state. A detector records a photon. A neuron records the detector. A notebook records the observation. Correlations spread outward. Reversing the event would require controlling every environmental degree of freedom carrying the record. The past becomes stable because information has proliferated. This suggests that classical reality itself may be partly historical. Certain states become robust because many fragments of the environment carry redundant information about them. Light scatters from a chair into walls, eyes, cameras, and air. Countless systems agree on where the chair is. Quantum Darwinism is one framework describing how particular stable states are effectively selected and copied into the environment. The shared present world may be the set of facts that have left enough records to be independently accessed. Time, information, and objectivity meet. Yet quantum experiments can blur ordinary temporal order. In some carefully designed situations, quantum processes can be placed in a superposition of different causal orders. Instead of event A definitely occurring before event B or B before A, the experimental arrangement can make the order itself quantum-controlled. These experiments do not allow a person to rewrite history or send messages into their own past. They explore situations in which classical causal order is not fixed in the usual way. The result hints that causal structure may be less rigid at the quantum level than in everyday spacetime. There are also delayed choice experiments, inspired by John Wheeler, in which the measurement arrangement is selected after a quantum system has entered an apparatus. Popular accounts sometimes say that the later choice changes what the particle did in the past. The careful conclusion is quieter. The experiment does not support one classical story in which the particle had already decided to be a wave or particle before the final measurement context was established. Quantum theory assigns probabilities to the entire arrangement. It does not require the past to be physically rewritten. The temptation to describe these experiments as backward causation comes from demanding an ordinary path, where quantum theory offers only amplitudes and correlations. Time reversal itself has several meanings in physics. One meaning is reversing velocities in an equation. Another is applying a mathematical time reversal transformation to a quantum state. Another is watching a recorded process backward. Another is asking whether nature treats past and future symmetrically at the most fundamental level. These are related but not identical. Most basic interactions appear highly symmetric under time reversal, but the weak nuclear interaction shows subtle violations. Certain particle decays distinguish between time directions in a precise microscopic sense. Through the broader CPT theorem, the combined transformation of charge, parity, and time has a central role in relativistic quantum field theory. Microscopic time reversal violation is real, but it does not by itself explain why eggs break, people age, and memories point backward. The enormous thermodynamic arrow still depends primarily on statistical behavior and boundary conditions. A tiny asymmetry in particle physics is not the reason cream mixes into coffee. This distinction protects the story from a common simplification. Time has more than one arrow. There is the thermodynamic arrow of entropy, the psychological arrow of memory, the cosmological arrow of expansion, the radiative arrow of outgoing waves, and subtle microscopic symmetry violations. They align in our experience, but they need not be identical in origin. The expansion of the universe itself does not automatically cause the thermodynamic arrow. A contracting universe would not necessarily make broken glasses reassemble or memories run backward. Entropy can continue increasing during contraction depending on conditions. The direction of time is not simply the direction in which space gets larger. If the universe someday stopped expanding and began contracting, observers would not necessarily experience life in reverse. Hearts would not beat backward. Ash would not leap into stars. The thermodynamic arrow would follow the statistical state, not the sign of the cosmic scale factor alone. Another question waits at the edge of relativity. Can time form loops? General relativity permits mathematical solutions containing closed time-like curves. A traveler following such a path could return to an event in their own past. Rotating universes, infinitely long rotating cylinders, certain wormhole arrangements, and the regions of idealized rotating black hole solutions have all been associated with such curves. A mathematical solution is not the same as a physically realizable machine. The required structures may involve unrealistic matter, unstable configurations, inaccessible regions, infinite cylinders, or conditions that quantum effects destroy. No observation shows that travel into the past is possible. Still, the equations do not dismiss the question as easily as common sense might prefer. Past-directed time travel creates paradoxes. The famous grandfather paradox asks what happens if a traveler prevents the conditions leading to their own journey. The bootstrap paradox imagines information or an object circulating through a loop with no clear origin. A scientist receives a formula from their future self, publishes it, and later travels back to provide the same formula. Where was the idea created? Several logical responses exist. The Novikov self-consistency principle allows only events that fit one consistent history. A traveler can participate in the past, but cannot produce contradiction. Attempts to change known events become part of the causes that made those events happen. Branching world approaches suggest that traveling to the past might lead into a different branch, preserving the traveler's original history while creating another. Whether any actual theory permits this is uncertain. Chronology protection, a phrase associated with Stephen Hawking, proposes that physical laws prevent macroscopic time machines from forming. Quantum fields near the threshold of a closed time-like curve may generate effects that destabilize the geometry, although a complete quantum gravity treatment is missing. Nature may protect causality before paradox can arise. Wormholes provide the most popular hypothetical design. A wormhole is a shortcut connecting two regions of spacetime. If its mouths could be held open and one mouth experienced a different amount of time through motion or gravity, the two mouths might become time-shifted. Passing through could connect different dates. But traversable wormholes appear to require exotic stress-energy conditions, and there is no evidence that usable wormholes exist. Even if microscopic quantum structures resemble wormholes in some theories, turning them into stable passageways is another matter entirely. The quiet scientific answer is that travel into the future is real and measured, while travel into the past remains speculative and may be impossible. Every airplane passenger, astronaut, mountaintop clock, and satellite follows a slightly different duration into the future. The differences are usually tiny. High speed or extreme gravity could make them large. No known method returns a person to yesterday. The ordinary past has another kind of inaccessibility. Even without paradox, it cannot be revisited because its complete microscopic state has dispersed into the universe. To restore a room exactly as it was 1 hour ago, one would need to reverse air currents, photons, neural states, heat flow, chemical reactions, and every interaction with the surroundings. Information has radiated outward at light speed. Some has entered the body. Some has left Earth. The past is not merely behind a locked door. Its traces have been distributed into an expanding causal network. Memory recovers only fragments. This explains why remembering is reconstruction rather than playback. The brain does not store a perfect microscopic copy of an event. It stores selected patterns shaped by attention, emotion, knowledge, and later experience. Each retrieval can modify the memory before it is stored again. The felt past is therefore both real and edited. Photographs seem more objective, yet they also preserve one angle, one wavelength range, one exposure, one instant chosen by an apparatus. Every record is partial. The complete past may be encoded in principle in the present state of the universe if microscopic evolution is information preserving, but recovering it would require impossible control and knowledge. Practical irreversibility can coexist with fundamental reversibility. This difference between in principle and in practice is central to time. A law may permit reversal while probability forbids it for all realistic purposes. Information may be preserved globally while becoming unrecoverable locally. All events may form one space-time block, while consciousness experiences sequence. Time is where levels of description collide. At one level, a clock counts. At another, geometry determines proper time. At another, entropy creates direction. At another, memory creates passage. At another, quantum gravity may eliminate external time. No single metaphor can hold all of this. The river metaphor captures flow but suggests one universal current. The dimension metaphor captures geometry but can hide becoming. The clock metaphor captures measurement but not direction. The arrow captures asymmetry but not duration. Perhaps the difficulty is not that time is unreal. Perhaps it is that the word time compresses several structures into one familiar sound. Language does this often. The word heat once seemed to name a substance. Modern physics understands heat as energy transfer associated with microscopic motion and distributions. The word life names metabolism, reproduction, evolution, regulation, and information without reducing easily to one feature. Time may be similarly layered. The oldest philosophical arguments already sense the problem. Heraclitus emphasized change, the world in flux. Parmenides argued that change and becoming could be deceptive, because what truly is cannot arise from what is not. Zeno's paradox has challenged motion by dividing a journey into endlessly smaller intervals. Aristotle connected time with change and number, describing it through before and after. Augustine later asked what time was, and observed that he seemed to know until someone asked him to explain it. He wondered how past and future could exist when the past is gone and the future has not arrived, leaving only a present that itself seems to vanish. The puzzle survived because it was not created by insufficient clocks. Better clocks made the puzzle sharper. Newton gave time independent flow. Leibniz argued that time expresses relations among events. Kant treated space and time as forms through which the mind organizes experience rather than ordinary properties learned from objects. Einstein transformed time into observer-dependent geometry. Boltzmann connected its arrow to statistics. Quantum gravity reopened the question of whether it exists fundamentally at all. Each answer preserved part of the earlier intuition and removed another. There is still a practical reason the present feels special. The present is where action occurs. A person cannot change a remembered event directly. A person cannot yet act on a remote future situation except through choices made now. Sensory information arrives now. Muscles respond now. Decisions integrate memory with prediction in a moving window. The brain evolved to control a body, not to contemplate the entire block universe at once. Its present is the control surface where incoming evidence meets possible action. This may explain why the present feels illuminated even if physics contains no universal spotlight. The feeling of now is biologically indispensable. An organism must distinguish what has already happened from what can still be influenced. Agency lives at the boundary between record and possibility. The future seems open partly because knowledge is incomplete. Quantum mechanics may add genuine indeterminacy, depending on interpretation. Complex systems are sensitive to initial conditions. Human decisions emerge from processes too intricate to predict in full. Even a deterministic universe can be practically unpredictable from within. Not knowing the future is not the same as the future having no structure. But for a living agent, uncertainty is real enough to guide behavior. Prediction itself changes outcomes. A storm warning leads to evacuation. A medical forecast leads to treatment. A person's expectation changes their choice. In systems containing decision makers, knowledge of a prediction becomes part of the system. The future cannot always be observed without being influenced. This reflexivity helps separate physical determinism from fatalism. Fatalism says outcomes occur regardless of actions. Determinism, if true, would include the actions as causes. Choosing to move away from danger is part of the chain producing survival. A complete space-time description would contain decisions, not bypass them. Whether freedom requires indeterminism is a philosophical question beyond experimental physics. Randomness alone does not create meaningful choice. A decision produced by a random particle would not automatically be freer than one produced by reasons, values, memory, and neural activity. Time makes choice possible as a process, but physics does not tell us the only correct way to interpret agency. There is another gentle clue in the word duration. Duration is always duration of something. A note lasts. A planet orbits. A particle decays. A body sleeps. Empty mathematical time can be represented, but measured duration belongs to processes. Henri Bergson distinguished measured clock time from lived duration. For him, conscious time was not a row of identical units placed side by side. A melody is not experienced as isolated notes occupying separate boxes. Each note carries what came before and changes the meaning of what follows. Memory enters the present, and anticipation reaches toward the future. This difference became public in Paris in 1922 when Bergson and Einstein met during a discussion at the French Philosophical Society. By then, Einstein's relativity had transformed physics, while Bergson was one of Europe's most celebrated philosophers. Their encounter is often retold as a contest in which one defended subjective time and the other declared that only clocks mattered. The actual disagreement was more subtle. Einstein's theory answered operational questions. If clocks move differently or occupy different gravitational conditions, what readings will they show when compared? Which distant events are simultaneous within a specified reference frame? These questions have experimental answers, and personal feeling cannot alter them. Bergson worried that the success of this measurable time might be mistaken for a complete account of duration. Waiting, listening to music, remembering childhood, grieving, becoming bored, and sensing a moment pass are not exhausted by the statement that a clock advanced 60 seconds. The unit is identical, the experience is not. Relativity did not make lived time false. It showed that physical time was already less simple than common sense believed. Bergson's philosophy did not make atomic clocks subjective. It asked what remains when measurement is separated from experience. The two projects can be allowed to coexist without pretending they answer the same question. Physics describes space-time intervals and the behavior of clocks. Neuroscience and psychology investigate how brains construct sequence, duration, memory, and anticipation. Philosophy asks how those descriptions fit the first-person fact of living through change. A minute in an equation and a minute beside a hospital bed share a unit, but not a human meaning. Subjective time is not a defective copy of clock time. It is another biological phenomenon, constrained by physical processes but shaped by attention, emotion, memory, and expectation. When danger appears, the brain increases attention and encodes detail. Stress hormones alter memory. Rapid sampling may create the later impression of expanded duration. In flow states, self-monitoring decreases and clock awareness fades. During meditation, time may feel spacious or absent. During dreams, long narratives can seem to unfold within short intervals, though dream duration research suggests complex relationships rather than unlimited hidden hours. Under anesthesia, time can vanish from experience. One moment is the preparation. The next is recovery, despite an hour having passed on clocks and in the body. This absence is different from sleep. Sleep often contains dreams and changing brain states. Anesthesia disrupts consciousness through pharmacological effects on neural communication and integration. The missing interval leaves no felt duration because no memory bridge was formed. From the first-person view, experience time depends on consciousness and memory. From the third-person view, physiology continued. The heart beat through an hour the mind never possessed. This difference raises a thought experiment. If a universe contained change, but no conscious observer and no memory system, would time pass? Physics would still describe intervals, causal structure, decay, motion, and entropy. In that sense, time would remain. But there would be no felt passage, no waiting, no present experience that's special. Flow may require a mind, even if temporal structure does not. This balanced answer avoids two extremes. Time is not simply invented by consciousness, because clocks, particles, and gravitational systems behave temporally, without human observation. But the sensation of time flowing may be constructed by conscious systems that remember and anticipate. The river may be in us. The riverbed may be in physics. A similar distinction applies to color. Electromagnetic wavelengths exist without vision. The experience quality of blue depends on a nervous system. Color is neither a meaningless illusion nor a property identical to wavelength alone. It emerges from a relationship between world and observer. Perhaps temporal passage is relational in a similar way. The universe provides ordered events, durations, causal structure, and entropy gradients. A brain transforms them into yesterday, now, and tomorrow. This transformation is not arbitrary. It is constrained by reality. A brain cannot choose to remember tomorrow in the ordinary way because records arise from past interactions. It cannot make a low clock run faster by wishing. Subjective time is flexible, but not free from physics. The mind interprets a temporal world. It does not create the entire world from nothing. Calendars reveal another meeting between nature and convention. A day is tied to Earth's rotation and a year to Earth's orbit, but the cycles do not divide neatly into one another. The tropical year is a little less than 365 and a quarter days. A calendar using only 365 days would drift slowly away from the seasons. The Gregorian rule adds a leap day and years divisible by 4, omits it in most century years, and restores it when the year is divisible by 400. February receives an extra day because the sky refuses to fit human arithmetic perfectly. Months preserve an older compromise with the moon. A lunar cycle is about 29 and a half days, while 12 such cycles fall short of a solar year. Different cultures created lunar, solar, and lunisolar calendars, sometimes inserting an additional month to keep seasons and months aligned. The week, unlike the day and year, has no equally direct astronomical cycle. It is a social rhythm made durable through shared practice. Civil time also negotiates between two imperfect partners. Atomic time is extraordinarily regular. Earth's rotation is not. Leap seconds have occasionally been inserted into coordinated universal time so that civil clocks remain close to the turning planet. The added label 23:59:60 is tiny, but computer networks dislike it because many systems assume every minute contains exactly 60 seconds. International metrology is now moving toward a more continuous UTC in which a larger difference from Earth's rotational time can accumulate instead of being corrected through frequent 1-second jumps. The implementation requires coordination because communications, navigation, astronomy, software, and law all use time differently. The same problem becomes larger beyond Earth. A Martian solar day lasts about 24 hours and 39 minutes. Lunar surface clocks differ from terrestrial clocks because motion and gravity differ. Messages between planets require minutes or hours, making a shared conversational present impossible. A future interplanetary civilization will not discover one natural solar system time. It will construct coordinate systems connecting many local proper times. Humanity may return to something resembling the age when every town kept its own noon, except that the towns will be worlds. The body also carries more than one kind of time. Chronological age counts years since birth, while tissues record different histories. Bone stores mechanical load. Antibodies store earlier encounters. A scar stores injury. Neural connections store experience. Blood renews continually, while many neurons persist for decades. Researchers build statistical measures called epigenetic clocks from patterns of DNA methylation that change with age. These tools can estimate chronological age and may capture aspects of biological aging, but they are not literal clocks hidden inside cells. Different tissues, diseases, environments, and methods produce different readings. No single number contains the complete age of a living body. Biology moves forward by incorporating history rather than returning to an untouched state. A healed bone is not the bone from before the fracture. A learned skill leaves altered circuits. Recovery creates a new present shaped by what happened. Evolution does the same across generations. Mitochondria preserve an ancient partnership with bacteria. The path of the recurrent laryngeal nerve preserves changes in the bodies of distant ancestors. The elements in blood and bone preserve stars that lived and died before Earth formed. Deep time is not merely behind the body. It is built into it. This accumulation gives the arrow of time a creative side. The future differs from the past not only because structures decay, but because systems acquire records, adaptations, relationships, and new levels of organization. Stars enrich galaxies with heavier elements. Chemistry becomes biology. Nervous systems create memory. Cultures preserve knowledge outside individual brains. A reversible microscopic equation can coexist with irreversible history because large systems form stable patterns at new scales. Temperature is real, even though no single molecule carries a temperature by itself. A wave is real, even though the water does not travel across the sea with the shape. A traffic jam can move backward while every car moves forward. The word emergent does not mean imaginary. If temporal direction, duration, or even space-time itself emerges from deeper relations, time can remain real at the level where clocks compare, organisms age, and memories form. A melody offers a gentler image. No single note contains the song. The pattern exists through ordered relations among notes, and the listener's memory carries earlier sound into the present one. Time may be less like a substance poured through the universe and more like the structure that allows the melody to exist. Physics even contains phases called time crystals. The name does not mean time has frozen into a jewel. In certain driven quantum systems, collective behavior repeats with a period related to but distinct from the external drive. The system displays temporal order, just as an ordinary crystal displays a repeating structure in space. Time crystals do not provide perpetual motion or a route into the past. Their importance is that time can participate in symmetry. If the laws governing an isolated experiment are unchanged when the entire experiment is shifted to another moment, the laws possess time translation symmetry. Emmy Noether showed that continuous symmetries are connected to conservation laws. Spatial translation is linked with momentum, rotation with angular momentum, and time translation with energy. Energy conservation is therefore tied to the fact that an isolated experiment follows the same laws whenever it is performed. The relationship becomes subtler in an expanding universe, where space-time may lack one global time translation symmetry. A photon's wavelength stretches as the universe expands, and the familiar idea of one globally conserved total energy may not apply in the same simple form. An ordinary clock also reveals a small tension between symmetry and record. Its reference process must repeat, but its complete state must not return unchanged. A pendulum can revisit the same position, yet gears or electronics preserve how many cycles occurred. Without a counter, the first swing and the 1000th would be indistinguishable. A clock needs repetition and memory. The atomic transition used as a reference can be highly reversible, while preparation, measurement, feedback, storage, and communication create records and release heat. Real clocks participate in the thermodynamic arrow even when their repeating core is exquisitely regular. Duration becomes observable when change leaves account. This brings us to a strange practical fact. The more accurately clocks measure relativity, the less meaningful it becomes to speak of their height without knowing gravity. A clock's frequency depends on gravitational potential. To compare the best optical clocks across distant laboratories, scientists must know elevations and gravitational fields with extraordinary precision. Tides from the moon and sun, atmospheric pressure, groundwater, and movements of Earth's crust can matter. Time metrology becomes geophysics. A clock is no longer only a device for measuring time. It measures where it is in curved spacetime. If two ultra-precise clocks disagree, one may not be wrong. One may be higher. The idea of a perfect universal clock dissolves into a map of local conditions. Yet local proper time remains wonderfully stable. An observer beside an ideal clock always finds normal ticking. The laws of chemistry work. The heartbeat feels ordinary. Relativity does not make life locally chaotic. The strangeness appears through comparison. This is a recurring theme in modern physics. Many quantities are not absolute properties of one object alone. Velocity is relative to a frame. Electric and magnetic fields can mix under changes of motion. Simultaneity depends on an observer. Entanglement belongs to relationships between systems. Time may be less a substance possessed by the universe than a structure of comparisons. Carlo Rovelli and other relational thinkers have emphasized that physics describes how variables change relative to one another. A pendulum angle changes relative to a hand position. A planet's position changes relative to a clock reading. A quantum field changes relative to another degree of freedom chosen as a clock. There may be no need for an invisible variable called universal time flowing behind every relation. But eliminating universal time does not eliminate sequence. Events can still be ordered causally. Processes can still have durations. Clocks can still disagree predictably. The relational universe is not timeless in the ordinary sense. It is full of local times. A railway timetable sought one common time for a country. Relativity says the universe cannot be organized so simply. Still, synchronization remains possible within chosen reference frames and with known corrections. Engineers define coordinate times that make navigation and astronomy manageable. These time coordinates are tools adapted to particular systems. The flexibility does not mean physics is subjective. Once the frame and procedure are specified, predictions are exact. Relativity replaces one universal answer with transformation rules connecting many valid answers. This may be a more mature kind of objectivity. Reality is not what one privileged observer sees. Reality is the structure that allows all observers' measurements to fit together consistently. Space-time is the pattern beneath disagreement. The same lesson applies to the present. There may be no universal now, yet each local observer has a well-defined event here and now. Nearby observers can synchronize approximately. Communities create shared presence through communication and convention. A live broadcast feels simultaneous across a country, although signals require time and servers add delay. A conversation feels immediate across a room, although sound travels and brains process. Human now is a region of tolerated difference. Technology narrows or widens that region. A century ago, a message crossing an ocean took days or weeks. Today, light carries it in a fraction of a second through cables, though routing and processing add delay. Markets, games, scientific instruments, and conversations operate across coordinated timestamps. Civilization has built a synthetic present around the planet. It is not perfectly simultaneous in Einstein's sense. It is synchronized well enough for shared action. This may explain why the loss of simultaneity in relativity feels more dramatic than it is in daily life. Human communities never possessed exact universal simultaneity. They constructed increasingly precise approximations. Physics simply revealed the limit no technology can remove. Light speed is not only the speed of a particular messenger. It is built into causal structure. Signals cannot connect space-like separated events through ordinary means. The universe has a maximum speed for influence. This creates horizons. The observable universe is limited not necessarily by a physical wall, but by how far light has had time to travel through an expanding cosmos. There may be regions whose light has never reached us. Some regions we see today may send future signals that never arrive because expansion carries them beyond our cosmic horizon. The universe can contain events that are forever absent from our future knowledge. Time limits observation. Black hole horizons are another version. An event beyond the horizon cannot send a signal outward. The information may remain part of the full quantum state in ways connected to the black hole information problem, but no ordinary message returns. A horizon is a boundary made from causal time. The earliest universe also presents a boundary. Asking what happened before the Big Bang may be meaningful in some cosmological models and meaningless in others. In the simplest classical extrapolation, space-time itself reaches a singular limit, and the ordinary time coordinate cannot be extended reliably through it. Saying that time began at the Big Bang is possible within some descriptions, but it should not be treated as an experimentally settled sentence about an absolute beginning. Quantum cosmology may replace the classical singularity with a bounce, a no-boundary condition, an emergent phase, or something not yet imagined. Current physics does not know whether there was a before in the familiar sense. The question may resemble asking what lies north of the North Pole, as Stephen Hawking and others suggested in particular models. The answer is not another location because the coordinate itself ends, but other models contain an earlier contracting phase or a broader structure. The honest boundary is uncertainty. The future boundary is uncertain too. Dark energy drives accelerated expansion in the current cosmological model, but its nature remains unknown. If it behaves like a cosmological constant, expansion continues indefinitely. If it changes, other futures become possible. Time may extend without end, terminate in a singular event, cycle, branch, or lose ordinary meaning in equilibrium. The universe has not told us its final schedule. Even infinity needs care. Infinite future time does not guarantee infinite meaningful events accessible to one observer. Horizons, decay, entropy, and finite resources matter. Conversely, finite proper time can contain unbounded coordinate descriptions near horizons. The phrase forever depends on the path and clock. This returns us to the traveler near a black hole. A distant coordinate system may assign an infinite time to reaching a horizon, while the falling traveler's proper time remains finite. Neither description is simply the real one and the other false. They answer different questions using different coordinates. Coordinate time can behave strangely without local physics becoming singular at the horizon. A map can place the North Pole at an edge or distortion depending on projection. The geography remains. Coordinates are tools, not terrain. Relativity teaches caution whenever a time coordinate appears to stop, diverge, or reverse. One must ask whether the effect belongs to physical invariance or to the chosen map. Proper time, causal order, curvature, and observable signals provide the firmer ground. The same caution applies to statements that time slows down. Locally, every ideal clock ticks normally. The phrase means that clocks following different paths accumulate different elapsed times when compared. No one feels their own second becoming longer. A traveler moving near light speed does not watch their thoughts slow. The distant universe may evolve differently relative to them, and reunion reveals an age difference, but local experience remains ordinary. Relativity is strange through relationships, not through local malfunction. Perhaps this is comforting. The universe does not require one universal rhythm for every place. It allows each path its own duration while preserving consistency. A heartbeat is local truth. The room tonight has its own proper time along Earth's rotating, orbiting path through space-time. The planet moves around the sun. The solar system moves through the galaxy. The galaxy moves within larger structures. There is no state of absolute rest against which the room's true motion can be measured. Yet the clock beside the bed remains valid locally. Motion relative to different objects can be calculated. Proper time along the room's path can be measured. There is no need for the universe to provide a hidden stationary background. This is another quiet achievement of relativity. It removed the demand that motion be judged against invisible space. Time and motion became relational, but not arbitrary. The question, is time actually real, can now receive one answer, though the answer has several layers. The universal river imagined by Newton is not supported by modern physics. There is no single cosmic clock whose present moment reaches every place at once. Motion and gravity alter the durations accumulated along different paths. Observers can disagree about distance simultaneity without either making an error. But this does not make time unreal. Proper time is real enough to leave twins with different ages after different journeys. Gravitational time dilation is real enough to alter satellite clocks and positioning systems. Causal order is real enough to determine which events can influence one another. Entropy is real enough to make a shattered glass remain on the floor. Atomic transitions are real enough to define the second. Biological rhythms are real enough to change sleep, temperature, hormones, and metabolism. What may be absent is not temporal structure, but one universal flow added on top of every process. The feeling of passage may arise because a living brain changes while preserving incomplete records of earlier states and preparing actions for states that have not yet arrived. The past is remembered because it has left physical traces. The future feels open because its traces are not present in the same form, and because knowledge from within the universe is limited. Flow can be emergent without being meaningless. A wave is emergent from moving water, yet it can cross an ocean and move a boat. Temperature is emergent from molecular motion, yet it can melt ice. A melody is emergent from a sequence of notes, yet it can remain in memory for a lifetime. The fact that something is not fundamental does not remove it from reality. Time may be one of nature's layered facts. At the deepest level, there may be quantum relations, causal order, geometry, or something not yet understood. At the level of relativity, world lines contain proper duration. At the level of thermodynamics, entropy gives macroscopic history a direction. At the level of life, circadian clocks coordinate chemistry. At the level of consciousness, memory and prediction create the lived present. No layer has to pretend it is the only one. Calling all time an illusion would leave too much unexplained. An illusion must begin, persist, and end. A brain producing it must change from one state to another. The claim quietly borrows the sequence it tries to remove. A more careful conclusion is that time is real, but not as one substance flowing identically through the universe. It is real as relation, duration, causal order, asymmetry, and history. The room tonight has followed its own world line while this story unfolded. Earth rotated slightly. The planet continued around the sun. The solar system moved through the galaxy. Satellite clocks gained and lost tiny fractions relative to clocks below. Photons crossed distances. Heat spread. The body used energy and altered its internal state. No master clock commanded these events to advance together. They remained connected through local laws. Somewhere, an atomic clock compared an oscillator with a quantum transition. Somewhere else, a radio telescope may have received the pulse of a rotating neutron star. A memory formed because neural connections changed. A warm surface released energy into cooler air. Each process carried its own rhythm, and comparison turned those rhythms into measured duration. The clock nearby did not pull the night forward. It simply changed and remembered how many times it had changed. The body has its own useful clocks. Breath follows breath without perfect regularity. The heart varies gently from beat to beat. Molecular feedback loops track the biological night. Sleep pressure reflects the chemistry accumulated during waking. These systems do not need to resolve the block universe or quantum gravity before they can guide the body toward rest. Life measures the time it needs. A wound does not heal because hours exert a force. Cells divide, vessels grow, inflammation resolves, and tissue reorganizes during those hours. A skill does not appear because a calendar advances. Practice changes circuits. A mountain does not erode because time pushes it. Water, wind, temperature, gravity, and chemistry act, while clocks compare the transformation. Perhaps time does not do things. Things happen, and their relations create time. That thought can remain open rather than final. Physics has not completed a quantum theory of gravity. The origin of the universe's low entropy beginning remains unexplained. The nature of dark energy is unknown. Conscious experience is not fully understood. Presentism, eternalism, relational time, and objective becoming continue to be debated. The unanswered part is genuine, but it does not disturb the local night. Here, the next event can be only the next breath. Air enters, pauses briefly, and leaves. The interval is not a perfect scientific unit. It is a living rhythm, adjusted by the brainstem and shaped by the approach of sleep. The mind may still notice a clock, but it does not need to follow every count. Attention can loosen before the clock stops. A person can sleep through hours that later seem to have vanished. Although the body has continued through changing stages, neural rhythms, temperature shifts, memory processing, and repair, those hours are not empty. They simply belong less to conscious narration. The past does not need to be held in full tonight. Its traces already exist in memory, matter, light, and changed relationships. The future does not need to be calculated. It remains connected to the present through processes that continue without supervision. Relativity can keep its many local times. Entropy can keep its arrow. Atomic clocks can keep their count. Pulsars can turn in distant darkness. Philosophers and physicists can return to the question tomorrow. Nothing here requires one final metaphysical decision before sleep. The universe does not need to be synchronized by the mind. The clock carries no demand that you listen. For now, this local present is enough. Sleep well. Good night.